How you doing? My name is Marco Gramazio, and this is my fourth year pipe fitters project. I am doing waste to energy HVAC system, converting residential trash into heating and cooling for a three bedroom house. We will start with residential trash into gasification, into heat transfer, and then heating and cooling. The system overview and concept. Basic breakdown is process bath, waste, uh, downdraft gasifier into syngas and then into the burner slash heat exchanger. Then thermal oil loop moves to heat the house. Mode switch heating hydronic coil and or cooling absorption chiller. Um, throughput 5 to 10 kilograms a day household waste on average. Um, what is waste energy in HVAC or residential HVAC? Waste heat recovery is reusing heat that will otherwise be exhausted, ventilation, condenser slash refrigeration, wastewater. The goal of this is to reduce energy bills and CO2, improve comfort and indoor air quality. The approaches of this are heat HRVs and ERVs for ventilation, heat pumps recovering from air slash water slash wastewater and thermal storage. The energy savings are potentially around 20 to 50% of HVAC energy use through efficient heat and transfer reuse. The system benefits are the main subsystems: ventilation, HRVs and ERVs, heat recovery, heat pump, water to water or air to water, hydronic distribution, and DHW preheat and controls. Like I said earlier, the benefits are 20 to 50% savings for energy throughout the HVAC systems, and depending on the load and climate, better IAQ and peak load reduction, and also electrification ready. Typical sources slash things: condenser loop, exhaust air, wastewater, space heating, DHW, and reheat. Integrations opportunities combined with existing hydronic systems, solar thermal, ground source, heat pumps for maximum efficiency. Um, the key components I will be using in this are heat pump circuit, compressor, condenser, expansion device, evaporator, um, heat exchangers, plate type for wastewater heat recovery, runaround coils for exhaust air, and or shell and tube for high efficiency transfer. Hydronic system: the buffer tank, which holds the thermal storage, circulation pumps with VFDs, air separator, so we can remove the microbubbles, expansion tank, so we can regulate the pressure, and wash drainers for filtration. The ventilation, HRVs and ERVs, core wheel, ERVs, rated filters, silencers, dampers, with actuators for flow control. Terminal units we'll be using will be fan coil units, hydronic air handlers with pressure independent control valves, and room thermostats. Major component breakdown: waste processing, sort, dry, shred, with the hopper plus auger feed, variable speed feed mechanism, gasification reactor, downdraft, fixed bed, 600 to 700 degrees Celsius, normal, um, multi-zone drying, pyrolysis, oxidation, and reduction, syngas handling, air blower, dampers, cyclone filter, burner with flame monitoring, heat recovery, syngas, a thermal oil, heat exchanger, or hot oil pump, expansion tank, pressure relief. The distribution: three-way diverting valve for mode selection, hydronic coil for heating, and absorption chiller for cooling. For controls, we will be using PLC sensors, actuators, interlocks, CO2, smoke detection, emergency shutdown, and fire suppression systems. Basic process of waste gasification process: downdraft, feed path, hopper into the variable speed auger, airlock, and then reactor. And then the reactor zones: drying, pyrolysis, oxidation, and reduction, air control, blower, damper, actuator, maintain slight negative pressure, syngas cleanup, cyclone, plus the char bed filter, and tar management. Ash handling, seal with ash pod with high temp gasket to prevent that from overflowing. The heat recovery and thermal oil system, burner slash primary HX syngas combust, heat transfers the thermal oil shell into design. Like I said, operation range around 150 to 250 Celsius oil supply and a low pressure loop. Loop components, pump, VFD, expansion tank, relief valve, strainers. Instrumentation, we will do supply return, TET, DP across HX, flow switch, PT. Piping, we will use around inch and a half to 2 inch schedule 40 carbon steel and mineral wool insulation. Basically, this is a slight little breakdown of what I got, a little diagram. Um, Heating mode, operations, hydronic distribution, hot oil to water, HX, around 50 to 60 Celsius water supply. The air handler, hydronic coil, heat living zones, optional radiant zones. Um, Zone control, two-way valves with electric actuators, thermostats via PLC. The pumps, secondary water circulator, auto air vents, and expansion tank. The design example, peak 8 to 12 kilowatts to meet three bedroom load, theoretical. Um, Another basic breakdown of what the system could look like. Um, the cooling mode, absorption chiller, generator heat by hot oil, produces refrigerant vapor, absorber plus condenser, reject heat to condenser loop, dry cooler or tower. Um, Evaporator makes chilled water to AHU cooling coils. COP single effects around zero point 0.6, zero point 0.7. The loops were hot oil, chilled water, condenser water. Another basic diagram of the system and the components I have into it. The control valves I will be using are pressure independent control valves. Maintains consistent flow rates regardless of pressure fluctuations. Ideal for fan coil units and hydronic coils. Two-way modulating valves, primary control elements in variable flow hydronic systems regulate flow to terminal units based on load requirements. Three-way diverting valves directs flow between multiple paths used for DHW, priority control, or coil bypass in waste heat recovery systems. Isolation ball valves provides full shutoff capability at service points, pumps, heat exchangers, tanks, etc. Um, Enables maintenance without system drainage, which is good in case something bad happens. You can save the money um, without having to drain it all and then redo it again. Check valves prevents reverse flow in the system, critical for preventing ghost flow through idle pumps and parallel arrangements. And last but not least, but I will be using balancing valves. Adjust flow distribution throughout the system, ensures proper heat transfer at all terminal units. Um, some of the actuators I will be using are electric rotary actuators, three-way diverting valve, modulating dampers for air intake and syngas flow, zone valves for hydronic heat distribution, linear and pneumatic actuators, variable speed feed auger for torque monitoring, pneumatic emergency shutoff valves, fail-safe closed, linear valve positioners for precise flow control. Control loops and PLC with PIDs for reactor temperature, hot oil supply temperature control, chilled water supply temperature, and VFDs for blower, hot oil, and water pumps, and hot oil pumps. Sorry. HMI interface, touchscreen display for mode selection and monitoring, which sends real time trends for temperature, pressure, and flow, limit slash level switches with visual indicators, and you can receive notifications of the system through text messages and emails. The complete piping and system flow diagram, hot oil loop between 1.5 inch to 2 inch, schedule 40 isolation valves, check valves, strainers, expansion tank PRVs, hydronic heating size pipe I will be using is 3/4 to 1 inch copper/steel air vents, um, with air vents installed, two-way zone valves, pump with IFC. Chilled water I will be using 1 inch to 1.5 inch insulated piping to AHU coils, three-way control valve, add evaporator. Condenser water I will to dry cooler slash tower with fan, VFD, drain, and water treatment if wet. Instrument tags, of course, test ports, and gauges at all users. This is a basic, or not basic, but as complicated as I can get the system to look. It's color coded with the pipes I need: domestic hot water supply, return water, um, with heat, the waste heat exchanger, heat recovery, heat pump, buffer tank, with PRV1, HRVs, isolation ball valves, check valves, um, PICVs, temperature, pressure, differential sensors as well. Um, with this system, um, each season will most likely run different. Heat pump in the winter, the heat pump one recovers heat from waste source, DHW priority V, three-way valve, HRV, ER/ERV prevents or preheats outdoor air. FCUs modulate via PICVs. Summer operation can the heat pump can reject low grade heat to DHW tank, free hot water, while providing cooling, and the ERV manages humidity. And shoulder seasons, due to it being cold in the morning and hot in the afternoon/evening. Um, Simultaneous heating/cooling zones share heat variable flow, saves pump money, saves pump energy. Control strategy continues HRV and ERV at medium speed per code. Boost via occupancy, IAQ sensors, primary savings drivers, coincident heating and cooling loads, DHW integration, uh, pressure independent control valves, um, energy performance. Like I said a few times already, 20 to 50% HVAC energy savings depending on climate zone and building loads. So it may run different if you have it down south versus if you have it up north, or vice versa. The complete operation cycle: startup with pre-checks, establish draft, preheat oil, ignite burner, emit feed, steady state, modulate, feed air, select heating or cooling via three-way, mode switch, ramp and stabilize temperatures before divert and flow, shut down, stop feed, burnout tars, cool down, purge, ash removal, maintenance, daily ash, weekly filter check, and quarterly oil sampling. And the summary of and benefits and considerations: on site, the benefits would be on site reduction or waste reduction, diversion from landfills, potential fuel savings, reduce energy costs, resilient heating/cooling independent of grid, engineering highlights: hot oil loop for stable thermal transport, actuator driven controls for precise operation, integrated safety and monitor systems. Some of the limitations that the system may have is feedstock variability, affects performance, emissions slash permitting challenges in residential areas. Say if it's a tight area, might not work the best in apartment complexes and stuff like that, or just like densely populated areas. The maintenance requirements, it could be high strung and technical complexity. Some of the scalability options: hybrid with biomass pellets for consistent feedstock, um, integration with solar thermal for supplemental heat, and district microgrid tie-in for community scale slash or community scale waste management. Um, yeah, basically that's my project. Thank you very much.